Thanks very much. That's the best introduction I've had in a while. Wow, I'm not going to live up to that. As a pantheist, I believe that God walks among and inside all of us. So that's my position. This talk is actually about observability for platforms generally. So I kind of put a dad joke title, which I now regret. So it's not about helping you understand why your app's slow. It's about if you're in platform engineering, how do you find out that your platform's slow and debug those issues. So if you wanted to talk on app latency debugging, this is not it. Please go and see one of the other talks. Don't stay here and be like, oh, I didn't really want to see this, but I'm a bit embarrassed to leave. Use your legs, go for it. It's no problem at all. I don't want you to sit in a talk that you don't want to see. Having said that, this is what I'm going to talk about. I want to acknowledge there's actually a ton of, this is not me, this is not my work, this is the work of a ton of other people. This is the SRE team that I work on. Who's heard of SRE? Okay, most of you, but not all of you. So SRE is site reliability engineering. Site reliability engineering is applying engineering principles to operations, to managing systems. And so the idea is that instead of doing click ops, where you're clicking through stuff, you solve problems using engineering approaches like code and talking to developers. That's the approach we take. We do still hold a pager. So half of this team is in San Francisco, half of this team is in London. Our shifts are 10 a.m. to 10 p.m. in San Francisco. Then we hand the pager over to London, where it's 6 a.m. They hold the pager to 6 p.m. And when we get paged, we get told something very cryptic, and then we have to go and work out. Firstly, how bad is it? Is it something bad? How many people it impacted? Then create an incident if it's something that is bad, that's impacting customers, and then try and get that fixed as quickly as we can. So that's the main part of the job, but the rest of the job is engineering and trying to make our systems more operable, more resilient, more scalable, and do the best thing fundamentally for our customers. So all these people have helped in putting together this material and operationalizing it. So I'm talking about a technique or an approach to thinking about platform reliability, but none of that stuff is any good unless it actually helps people in real life. So other people have talked about the importance of treating platform as product, and these are my customers as well. They're the people who actually, if it doesn't help them do their job, then why am I even doing it? There's also a team called Kraken here. This is the team that is part of SRE that helps try new approaches and design or come up with new ways of thinking about reliability. Two of the people here, Jeff and Narayan, created some of the slides that I've used in this presentation. There's a bunch of other people at Google and outside Google who've also given feedback on these ideas. Will Patterson here is the person who operationalized and implemented a bunch of the tools that I'm going to show you today. So I am SRE for the serverless platform, or this SRE team runs the serverless platform. What's a serverless platform? So, Kubernetes is great, but who here has actually managed or operated or been in charge of a Kubernetes platform? Okay, a bunch of you. So it's really hard work, and there's all kinds of things that require a lot of engineering and ops work. What if we didn't have to do that? What if you could just scale up and scale down to zero without having to worry about any of that? Well, that's what the serverless platform is. You can just deploy a container, and the platform takes care of scaling up as much as you want or scaling it down to zero. So it's pretty great, actually. I have a lot of fun working on it because it's when it's doing that, it's really amazing to watch. However, we're basically giving our customers the ability to create enormous amounts of stress on this platform. That's our business model. That's how we make money, by letting people come in and scale up to thousands, tens of thousands of instances in seconds. So it's a shared platform. We see that. We feel that impact. We have customers where that's actually part of their business model. If they're advertising sporting events, for example, the sporting event starts, suddenly you've got enormous amounts of traffic coming onto your platform. That has an impact. And there's a whole bunch of tools we use to see that and manage it, but it's actually a complex problem to deal with. Before I go any further, I want to talk at a high level about our architecture, just so you kind of understand the context for this problem. So we have, these are end users, right? These are users who are using apps deployed onto our platform. We also have customers who are actually the people deploying the apps. We have a control plane, so when you push a new container live on Cloud Run, or you deploy an app or a cloud function, that gets built if necessary, or at least put in storage. And then we have a data plane that is responsible as traffic comes in for spinning up instances. So we have jobs running on Borg. Most of this stuff runs on Borg. Borg is Google's internal scheduling system for workloads. And so we're running what's called app servers, which are jobs that host containers, that host instances on shared Borg. We've got a ton of those. This is not to scale. And so once you've deployed a container or a function or whatever, and traffic starts coming in, this is where those containers start spinning up and serving traffic. When traffic comes in, it first of all goes to a networking component near the user. So the user may be in a completely different part of the world from the container that's going to serve their traffic. So firstly, their request is going to go to this networking component near the user, and then it's going to be routed to another traffic component here, a networking component here that's near the app. And then this component here is in charge of actually working out where to send it. So if there's no instance currently running to serve that traffic, there's going to be some negotiation while a container starts up, and then traffic gets sent to that instance. If there's a whole bunch of instances, it'll pick one. If that particular app server is overloaded, it might push back so that the traffic gets sent to a different one. So there's actually quite a lot of work done in negotiating where to send traffic and how it gets served and so forth. So it's a ton of complexity in actually how this platform works. And for you as a customer of the platform, you know, my instance is here. It's like the total perspective vortex in the Hitchhiker's Guide to the Galaxy. It's one little point in this enormous amount of stuff, but it's very important to you, which means that it's very important to us too. Who here has worked on a platform and you've had one of the customers of your platform deploying apps say, oh, my app's slow, can you help me? Has anyone had that? Yeah, and I can see those people going, yes, I've had that problem, and now I'm very tired. Because it's really hard to diagnose. Like, there's so many things that could go wrong with your app. And in some cases, it's because you changed something, right? You might have changed some code, you might have changed some config, that might have caused the problem. But there's many things that could be that are nothing to do with the customer. So there might be some, I mean, there's always dependencies, right? Your instance is talking to a bunch of stuff. The platform your instance is running on is talking to a bunch of stuff. Those things can change their behavior. That happens all the time in complex systems. If that's not happening, that's actually a sign that something's wrong. There might be a change in traffic patterns to apps or other apps running on the same app servers or in the same region, and that can cause a lot of sloshing around that can change latency as well. We make changes to the platform all the time. Other teams make changes to the dependencies of our stuff on other parts of Google's platform. And those config changes might pass all the unit tests, but actually cause disruption down the chain because complex systems have emergent behavior. And even if your component's behaving fine, interactions with other components can cause problems that you couldn't have predicted. We do have issues where if an instance on an app server gets a ton of traffic, that's going to impact the behavior of the other instances on the same job potentially, or even in the same cell. That happens in the case of denial of service attacks, for example, and we have very robust protections for denial of service attacks, but you can, while those are kicking in, that might cause problems. Abuse is one example of where that happens. Abusive workloads can cause similar problems. And even just the way that we bin pack the app servers and put instances in different places, if that's suboptimal, traffic shifts can cause that to become suboptimal over time. In fact, that's pretty normal, and so that can cause shifts in behavior as well. So when that comes in, you're like, well, there's this huge menu of things that it could possibly be. How do I even know which one of them it is? So the main thing we care about fundamentally is our signal is customer tickets. So as a customer, you're going to find some problem, and if you can't work out what it is yourself, you're going to create a ticket. So as an on-call, I'm not just looking at pages, I'm also looking at customer tickets coming in. And if I get one customer ticket, then my first response is going to be, well, let's make sure they haven't pushed a new version or there isn't something in the customer's configuration that might have caused this problem. But once you start getting a whole bunch of pages coming in or a whole bunch of customer tickets coming in, at that point you start to think, well, it's probably not a customer problem. That's likely to be a platform problem. And so at that point, you really are starting to think, maybe I should create an incident. Once you have a bunch of customers who are giving you tickets, you're going to create an incident. And at that point, you've got to go to your observability. So we have a ton of logging in Google. This is one of the things that, as someone who worked for industry for 20 years before joining Google, coming to Google and just seeing the enormous amount of data available for me to use was really great. So we don't just have like regular logs. Our logs are stuffed full of structured data in the form of protobufs. So a single request that comes through our system is going to create an enormous amount of structured data with timestamps for every part of the system that it's passed through, information like what version of the app server was running when that request was served, and tons of other metadata. So we have just an enormous amount of metadata in our logs. We have this thing called F1, this query engine that we can just query all those different data sources from logs to other systems of record within Google and join across them and run requests, run queries against huge amounts of data. So it's actually very powerful. But in a sense, it's kind of overwhelming. We have not only those log files, every job that's running on Borg emits large amounts of metadata that gets put into Monarch, which is our in-memory global time series database. And that data gets used or consumed by Automon, which is our monitoring system where we can go and get lots of graphs and see what's going on. But that's kind of overwhelming. So what do you even look at when something like that comes in? SLOs are typically seen as the answer to this problem of how to find there's a problem. So SLOs is basically saying, well, you know, we don't want to go below a certain level of availability. Once we're below a certain level of availability, that's going to page us and tell us something's going wrong. But SLOs are actually problematic in the context particularly of latency. So I actually went and got some data from all the stuff running on the serverless platform. And this is looking at latency. So latency is along the x-axis here. And this is the number of requests on the y-axis. And you can see this is logarithmic. So the highest frequency for request latency is between 1 second and 10 seconds. But then we've got these buckets below this, and there's this bucket right at the end of requests that are between 1 millisecond and 10 milliseconds. And then we've got this long tail here of requests that take, you know, over 100 seconds. So just the enormous amount of variability that a request might take end to end. And this is measured from when you get to the networking component in the cell where the request is being served to when the response to that request exits. So the request gets to the cell where the instance is, the instance does whatever you're doing in your app and sends the request back and it exits back to the user. So that's the latency we're measuring here. Just an enormous amount of variance. So you can't put a threshold for an SLO. That's just impossible. So even detecting when there's a problem is already an issue, because what are you going to do? You know, something might go up in one of these buckets, but that could just be a shift in traffic, right? There could be more traffic coming to a particular endpoint, which might show up here, but it might have nothing to do with actually the platform behavior. So our first attempt to think about latency and platform behavior, we took just one subset or one phase of that full end-to-end latency. So we look at this thing called request delivery latency. So this is the time from when the request enters the cell where it's being served to when your app starts processing that request. And so already here we can get some interesting data. So you can see the y-axis here is the number of projects that are seeing a latency above the threshold that we've chosen for that request delivery latency. The different colors are different cells within that region. So a cell is like a logical partition in a set of data centers. So we have data centers in a region. Those are logically partitioned into logically independent sections. And because serverless is a regional platform, apps are hosted in potentially multiple different logical cells, so that if one of them goes down for some reason, we can still serve traffic from other cells within the same region. So these different colors are different cells within the same region. And you can see here's an excursion here where it's impacted multiple cells. So if I see that, I'm already thinking, okay, this might be a dependency within the region that is causing some kind of problem. It gives you some kind of clue as to what's going on. But it's only still telling you about some subsection of those things that could possibly go wrong. It's not telling you anything about, for example, if there's a change in the behavior of the gvisor, the container technology that we use, maybe that might have changed behavior. It's not going to tell you anything about dependencies that your app might rely on, because that's not captured in this particular phase of the end-to-end latency. So this is good. It gives you some information, but it's not giving you everything. And in particular, it's not actually representing the customer experience. One of the things that we really want to do when we're thinking of a platform is some kind of metric or measure that actually represents the customer experience end to end. Are we measuring something that's actually a good proxy for what customers are seeing? Because we don't want to be looking at graphs that are telling us different things from the customer experience, because we don't know if customers are feeling it. This is the problem with cause-based alerts, which is we have a lot of, and we have a lot of information on particular components of the system. And you see this all the time. Like who works in ops and gets paged for stuff in this room? Okay, like a few of you. You get paged for something, you're like, oh, well, the CPU is really bad on this set of boxes. Is it impacting customers? No, zero impact on customers. They're not noticing at all. So if you're getting these pages all the time, and half of them, you don't even know if it's got an impact on customer experience, it's very painful to actually work out if you should be doing anything about it or if you should just go back to bed. I mean, we don't do night shifts because we have London and San Francisco, but go back to dinner, let's say. So you want something that actually tells you if customers are experiencing pain. That's the first thing that we want to do. A second thing we want is to have a signal that we can combine across projects. So we can detect if it's how many projects it's impacting. That's the most important measure we care about when we're looking at the impacts for an incident, how many customers are experiencing a problem. That severity is going to influence how we respond to that particular incident. We want to be able to combine it across projects. We want to be able to see if it's within a particular cell or if it's impacting multiple cells, or the worst case scenario, if it's something that's impacting multiple regions. So this signal has got to be combinable across projects, across cells, and across regions, so we can reason about the global behavior of the service. As I say, we particularly care about anomalies that impact multiple customers, because that's what's telling us that it's a platform problem rather than just a customer problem. We want something that's cheap to compute. As you can imagine, we get an enormous amount of traffic, and so it's got to be super cheap to compute this thing. We can't do things that are computationally complex because it's just going to be overwhelming and it's going to cost us a lot of money in terms of the resources we're consuming to process the data. So that's a problem. And fundamentally, we also want it to be principle-based. Like when you look at this graph, what's this number? This number is based on, basically, it's empirical. It's based on experience. It's not based on any particular principles. So what are the principles that we care about? As a platform engineer, there's kind of three things that we think are important components of reliability. Firstly, obviously, availability. Is the service there? Availability is typically kind of a yes or no thing, but it can be pretty gray as well. But you want the service to be there and for customers to be able, or customer traffic to be able to be served. And then the second thing is, how effectively is that done? Is that done in a way that customers actually are satisfied with or not? And then correctness is the service behaving in the way that meets the specification? Is the service behaving as specified, or are unusual things happening? Not because it's not available, but because it's fully available and performing really well, but doing weird stuff. And so we have a number of different ways to validate each of these different components of reliability. For availability, there's a very simple thing you can do, which is counting the number of failed requests versus the number of successful requests, and the proportion tells you how available is your service. For performance, What we typically do is we have probers. So probers are known workloads. We just have an app that sends traffic to another app that we have both created and both manage. And those will typically be simple user journeys with predictable performance. And because the performance is predictable, we can look at like the P99 latency and see if there's an excursion there, and then we know that there's something wrong. So probers are really useful. That's the first thing we do when we spin up a new region, is create probers, and that'll help us check performance and correctness and availability as well. But that's our main way of validating performance because the workloads are predictable in the way they behave. And then correctness, we have a lot of tests. So testing is super important in Google. If as a developer I send a pull request or a CL, as we call it in Google, to someone else to review, if it hasn't got any tests and I'm actually making a change that's not a refactoring, I'm going to get a comment back saying, hey, please write a test to cover this. So we have a lot of tests, a lot of unit tests, a lot of integration tests. That's very important to us. But we also have canary analysis. So when a change goes out into production, we do canary analysis as it goes through pre-prod and then starts rolling out progressively to different cells. We do canary analysis to make sure that there's not a change in behavior that we weren't expecting. However, these can't capture all the possible problems. So for availability, what is actually an error? So there's 400s versus 500s, but sometimes you get a 500 because of like a customer problem, such as a malformed URL or something like that. Sometimes that can cause a 500 where you were expecting a 400. Errors are fundamentally subjective, and the subjectivity of that is expressed in multiple places throughout the stack. So as a request is popping back through different layers of the stack, you have to do a translation. You get an error back from some other layer. You have to work out if it's a user error or a system error. That happens multiple times as the request propagates back up through the stack. And each time a subjective decision is made, which might not be what you're expecting. So I think the idea that you can cleanly separate platform errors versus user errors in practice is actually much harder than that. Also, we have deadlines and timeouts, we have circuit breakers, and so a timeout could cause a 500, but that could not be due to actually a system error. It could just be due to like a latency problem. Malformed requests, as I say, that can cause issues in terms of the subjectivity of the errors, and then if people are retrying or if our systems are retrying, that can magnify errors and cause the proportion of 500s to go way up. That's actually disproportionate to the proportion of errors that are actually happening in the system. So just to say, there's all these other issues that make this signal not as clean as you would perhaps like it to be. In terms of performance, those SLOs are very much workload dependent, and we only have a very small coverage in terms of the total behavior of the platform. Necessarily, probers are testing a known path through the system that's very narrow. But actually, most user workloads are using a whole bunch of different features, and those features can combine in unpredictable ways where actually you'll see problems that couldn't be caught by any individual prober. So it only covers a very small part of the state space in terms of the behavior of the system as a whole. And then in terms of correctness, yes, pre-prod tests are vitally important. A lot of people talk about testing in prod for production systems. But testing in prod on its own is terribly dangerous and you shouldn't do it. You need to have pre-prod tests as well, but they can't capture everything. Production systems necessarily, there's emergent behavior, those systems interact in unpredictable ways. You're not going to be able to cover all the possible scenarios, again, for the same reasons that your probers cover narrow scenarios. Unit tests cover narrow scenarios as well. So you will definitely find problems in prod that you could not have captured easily, certainly using unit tests, and in many cases using integration tests as well. And as we say in SRE, hope is not a strategy. So with this in mind, how can we think about latency regressions in the context of platforms? From the perspective of a platform operator, what I have is just a ton of events. And those events, in the case of the serverless platform, are requests. So user requests to apps running on the platform. So these are all our requests. This x-axis is time, and this y-axis is latency. And this is not meaningful or tractable in any way that's useful to me as a platform operator. But if you think of the perspective of the customer, it absolutely is. So a customer workload often will have a very predictable signal. Certainly if my app is predictable in how it behaves, which is often a nice characteristic. And so platform customers who are running these workloads will have often a very clear idea if their workload is behaving as expected. And you can look at all of these different workloads, and they'll have different patterns, but those patterns will be consistent over time. They'll be self-similar. So that is really the key to thinking about how do we model detection for latency regressions, is thinking about the customer perspective. Customers have workloads that behave in a predictable way, and what you want as a customer is fundamentally that my workload behaves the same way tomorrow that it did today. I want my workload to behave the same way consistently over time. That's what I want as a customer. And so we can actually model that using statistics. So for each workload, what we can do is we can look at their latency here. This is binned on the x-axis, and this is frequency. This is actually a real workload. And what we can do is we can fit a curve to that workload. So this is a log normal curve. And we found log normal is actually a pretty good way to model customer workloads to give you good coverage, which I'll talk about in more detail later. But the important thing I want to emphasize over time is that characteristic. Sorry, the important thing I want to emphasize for this diagram is that characteristic, which is that the workload behaves tomorrow the same way as it does today. What we want is the shape of this curve to stay the same. That, in statistics, is known as stationarity. So that property is stationarity, that the curve that I fit to those events stays the same shape over time. And so what we can do is we can take the parameters for this curve, which is going to be like a mean and a standard deviation, and we can look at, we can model the workload, and then we can look at future requests and see if they fit this distribution or not. The way we do this at scale with this goal of detecting platform latency regressions is called the 2 sigma technique, for reasons that will become clear shortly. And I just want to emphasize, like, we didn't invent the idea of statistics applying to events. It's not some massive kind of Google invention, hey, we discovered statistics. What's novel is the application of this technique to latency regression in the context of platform engineering. So I gave a talk before about this and got told off for people thinking I was claiming that Google invented statistics, which obviously we didn't. So, 2 sigma technique. Fundamentally, our hypothesis is that workloads that behave predictably should continue to behave in the same way over time. Their performance should be consistent. So, how we actually operationalize this hypothesis is we take all our workloads and we partition them into cohorts. And the way we partition them into cohorts is we want that the cohorts should be self-similar over time. So how do we take our workloads and break them down in such a way that we have some kind of grouping, some group of events that will behave in this way? And so depending on your application, what your cohorts are is going to be very different. And then for each cohort, you build a performance baseline. You basically, the first prototype of this that we did, we just did this in SQL. We selected all the events, we grouped it by app version, in fact, and then we took all the requests over the last 30 days and we computed the mean and the standard deviation. And that's just some basic SQL. And then you can store those parameters, the mean and the standard deviation, in a database with an identifier for that cohort. And that's all the information you really need for actually modeling the baselines. Identifier for the cohort, what's the mean, what's the standard deviation. And then, as new events come in, you can take a bucket of those events over 15 minutes and compare the distribution of the events in that bucket to that baseline that you've got for that cohort and say, is it the same or has it shifted? So that's the basic technique. And then the result is, as requests come in, each of those requests, you can score it with a predicted likelihood, which is called the z-score, or z-score. I can say z-score finally. And then what you've got is a time series of those statistics where you can model the behavior over time and see if it's regressing or diverging or not. So here's our historical service data. As I say, this is all in logs. We can query those logs using SQL. We also have that data in Monarch, so we can query it using time series tools as well. But what we're fundamentally doing is we partition it into cohorts. Our cohorts are app versions. So every time you deploy a new version of your app, that's a new cohort for us. And those cohorts are going to behave in different ways. So here's a cohort here where you can model it quite nicely with a normal distribution. In fact, here's something with a bimodal distribution. And we actually originally discarded workloads that behaved like this because you can't model them with a normal distribution. We've just implemented something on the team where you use something called a box-cox transformation, and you can actually transform multimodal distributions into a log normal distribution, or in fact a normal distribution, so that you can still score it in the same way. So there are statistics to deal with that. But then you also have just very messy things that don't really fit anything at all, and we basically discard those. If the behavior of your app isn't predictable, then you can't really have any expectation of it, is our thinking. And so we kind of, we just ignore it because it's unpredictable. You can't know if it's behaving well, so we can't know if it's behaving well either. So you compute the baselines, you do the transformation to log normal, you take the parameters, the mean and the standard deviation, you put that with a cohort identifier into the database, that's your baselines. And then, as events come in, you've got current service data, and for each event that comes in, you basically compare it to the metrics that you've got, and you compute the z-score. So what's the z-score? The z-score is basically how many standard deviations away from the mean is the latency for that request. That's a z-score. So a z-score of 1 is 1 standard deviation away from the mean. A z-score of 2 is 2 standard deviations away from the mean. And then you can combine those z-scores into buckets. And the buckets are a collection of events over time. And you compute the proportion of those events that are over some threshold, which, for the purposes of this, we choose 2 sigma as the threshold. So if the z-score is above 2, that's a bad event. If the z-score is below 2, that's a good event. And a j-score is basically the proportion of events in your bucket that's bad. So j-score of 0.1, 10%, that means 10% of your events are bad, which means they're above your threshold that you've chosen for bad versus good. And the cool thing about this is, by transforming those latencies into z-scores, we now have a signal that's combinable, because we can combine z-scores across projects. We can combine z-scores across cells, we can aggregate them across cells and regions. We've got something which is telling us what proportion of our requests are bad versus good that's completely combinable. So we're no longer having to worry about setting absolute latency thresholds. Instead, we can set z-score thresholds and have an idea of what's good and bad that's combinable across projects, across cells, across regions. So just to recap, we're aggregating z-scores across workloads. We know the fraction of those workloads with z-scores that are above 2 in Windows based on times. We use 15-minute buckets. We use project-based buckets of 15 minutes as our basic unit, and then we can combine those. We expect statistically about 2 to 5% of events will be outliers based on just the statistics of a normal distribution. If we see a j-score above 10%, that's a sign that something is bad. So that's our kind of basic signal. If we're looking at a cell and we see that the j-score goes above 10%, that's a sign that something's bad, because the statistics of the requests coming in are diverging significantly from the statistics we expect based on our baselines. And the detection, again, like the SLO equivalent, if you like, is the proportion of workloads that are exhibiting some kind of latency regression. In terms of our graphs on our monitoring dashboards, this is the graph that we initially look at when we get an alert based on this particular data product. So what we're looking at here is this thing here. This is what we do basically is we take that per project J-score, and then we turn that into a distribution. So we've got a distribution of project J-scores, and then we look at the 50th percentile of that and see if the 50th percentile of that is moving. And so here what you can see is the 50th percentile project J-score is moving above 5%. That's a sign that something is quite bad. The buckets, the duration of the buckets is important because a lot of our projects are pretty low QPS. So in a low QPS project, in a 15-minute bucket, you're going to get a lot of projects that are going to give you 0 or 1. And so that's why we do the distribution on a per project basis. And then if in that distribution you see it go above 5, that's like a pretty clear signal that customers are detecting pain. And then we also have this 70th percentile, this is a 30th percentile line as well, that 30% of projects are experiencing J-scores of at least 30. So there's a smaller group of projects that are experiencing this really high latency regression. So that's a clear kind of confirmation that we've got a real problem. And like the reason I like giving these presentations is because I like to actually snapshot graphs from our monitoring and put them on slides. So this is super fun for me. I hope it's fun for you too. The next thing we want to do when we know there's a problem is work out how many projects are being impacted. What's the severity of this thing? Should I be declaring an incident? How severe is that incident? And that's going to determine what actions I take in response to that. You know, sometimes if we can just add capacity. In fact, we have systems that automatically add capacity. That's what we prefer to do. We really, very rarely will like cap projects because, you know, we like money. And our whole business proposition is serving customer requests. So capping projects is really bad. We very rarely want to do that unless we find it's an abusive workload. We want to add capacity wherever possible. Our systems will do that automatically. But sometimes we can't do that because there's no capacity left in a particular cell, or some particular cell's behaving badly. We need to drain the cell so that we can keep the rest of the workloads running. So the severity is very important for us to be able to work out what the appropriate action is to take. And so impact analysis is the next thing that you care about as an on-caller. We've got a problem, what's the impact of that problem? And so here what we can look at is there's this kind of noise floor that you can see of projects. So this is the number of projects on the y-axis if I hadn't had to blur that out for you. And then this is time. And you can see there's kind of a noise floor of projects. And this is basically because like we're fitting a curve. So the curve that we fit is an approximation. It doesn't actually match the exact event distribution. And we discard workloads, as I say, that are not predictable, but it's still never going to be a perfect match for the distribution. And that's what you're seeing here. And we have actually just recently developed a technique that helps us kind of get rid of that noise floor, but it's actually pretty complex in practice. And I don't have time to talk about it now anyway. But it doesn't kind of matter really, because what you can look at is the delta between the noise floor and what you see as the peak, and that's the number of projects impacted. So that's the next graph we come and look at. How many projects are being impacted? Then we work out the severity of the event. So at this point, I like to go through a few FAQs. This isn't the end of the presentation. This is just like, I know you're thinking some things. I want to get ahead of that. Firstly, people ask, you know, do performance metrics actually follow normal distributions? No, they don't. What we found with normal distributions is we've got about 45% coverage using normal distributions. When we move to log normal distributions, it goes up to about 60%. And then with the Box-Cox transformation, you can get up to about 70% of coverage. And you know, people worry about that. From the point of, for the problem we're trying to solve, which is do we have a latency regression on the platform, that is plenty. You can do that with like 10, 15% coverage for that particular problem. If you wanted to give stuff to customers, then you might want higher coverage, and that's great. But for our purposes, 60% coverage is more than enough. And even with that lower normal-based distribution of 45% coverage, that was totally fine. So no, they don't, but as long as enough of them do, you're fine. Secondly, how do you know if the approximations hold? Well, I'll come to that in a minute. Basically, we backtest it and we validate it against the distributions. How do you define cohorts? That varies. So for example, this technique was pioneered with BigQuery. BigQuery is a service where you send SQL and you get back result sets, and you would think, how would you even define cohorts? And so that's kind of an interesting problem, but they actually basically use combinations of features on the platform to define cohorts, and were able to actually get this to work really well. And that's where it was pioneered before it was used on the serverless platform. So it varies according to application. I think this technique is very widely applicable to all kinds of domains. So we're using it in serverless, but anytime you've got workloads where you can model them statistically and then aggregate to detect regressions, you're going to be able to apply this technique. So it's very widely applicable, but how you define cohorts is going to be very domain dependent. How do you deal with singleton or infrequent workloads? We discard them. If your workload is getting less than 20 QPS in a month, we ignore it. And then finally, the question that I care most about, that sounds great, Jez. It's a lot of stats words. Does it really work? So we went and backtested it. And this is always the coolest thing when you write like some enormous amount of SQL and then get a bunch of stuff out. And then you put a graph up, and then you look at another graph you've got, and you're like, wow, that's totally the same thing. Amazing, it works. So we basically got a list of all the incidents from the last few months, and we took the graphs that we had from them for things like request delivery latency, and then we lined it up against the stuff we produced in the prototype using the SQL, and it totally works. And there was times when we detected things using this technique, and they weren't there on these graphs, and we went and looked into it, and we found there was actually something going on, and that actually, as we kind of expected, the graphs we had were kind of the top of the iceberg above the ocean, and there was this big part of the iceberg below the ocean of things that were happening that we didn't know about because we didn't have a way to detect these latency regressions from a customer perspective. So bad news, things are worse than we thought. Good news, we actually know when it's happening now. That's really great, right? Yeah, it's like saying we're not going to test for COVID because we don't want to know if it's actually happening. Well, turns out that's not a good approach to public health. And it's also not a good approach to detecting regressions on your platform. So we got data. It finds problems we knew we had. It also finds problems we didn't know we had. So that's great. There are limitations to this. Firstly, you need stats words. Like if you've been paged and it's 6 o'clock in the morning in the UK, which is when the shift starts, and you can't remember what a J-score is, but you've got being paged like 5 times, that's not great in terms of incident response. So that is a disadvantage. Like I still have to do that. I'm like, oh, what does this graph actually mean? Oh, it's a J-score and there's the 50th percentile. Okay, that's bad, right? So there's that kind of mental thing that you've got to overcome when you're trying to interpret the graphs. And so a lot of that is training and just kind of getting used to it, but you have to invest in that to make sure it works because, as an operator, you've already got so much information in your head. You're like, oh, great, a completely new set of terms and graphs that I've got to learn when I get paged. That's never popular, so that's something you've got to be aware of. The cohort coverage, 40% to 60%, that's totally fine. Not 100%, doesn't matter in this application. And then, a feature, not a bug, but this is symptom-based. It's telling you customers are experiencing a problem, doesn't tell you why. You then have to go and start looking at all the other graphs and start evaluating hypotheses one by one. Is it this? Let's look at the graphs. No. Is it this? Let's look at the graphs. No. And typically you'll have a set of things that you've got to evaluate, and it's always the same things. Is it dependencies? Is it this thing? Is there a change? Is there a new binary release? Is there a new configuration change? So those are your first set of things, and you can typically find out within a few minutes if that's the case because you know where all those graphs are. And if it's not any of those things, you're in for a long day. But we're building tooling as well to look at correlations. I've got 5 minutes, I think, right? So it's a feature, but it's going to cause you problems. So just briefly, I'm going to look at a couple of other applications. What the BigQuery team have done, which is cool, is break up those phases and independently model each of them. So for example, if you get a regression, they can see very easily, oh, it's I/O time that's dominating this. This must be an I/O problem. So being able to break down the phases and model those independently is the next step on this journey, if you like. You can also actually do A/B tests using cohorts. So one team used this to model the behavior of workloads on different CPUs and see how different workloads behave on different CPUs, which is kind of interesting as well. So my point is there's tons of applications of this. This is just the beginning. But any time where you've got a problem similar to this, it's a great go-to. That's it. Oh, yeah, sorry, just some key things. We have a way to reliably detect and measure the impacts of platform regressions. That's been transformational for us. We can now predict customer tickets coming in. Like, that's always what you want. You don't want to find out that you have problems because your customers are opening tickets. You want to find out you have problems because you know you've got problems, so when customer tickets come in, you can say, oh yeah, we know that's happening. This is what we're doing. Customers want to find out by looking at your dashboard that something's wrong, not have to raise tickets. Reliability fundamentally is a shared property. And so being able to reconstruct end-to-end customer behavior is really important. We have a way of making those metrics combinable so that we can analyze at the project level, at the seller level, at the region level. What customers care about is not the actual behavior, but is that behavior changing, which is what this technique models. Distributed systems, one of the characteristics of them is they produce decorrelation. Where there's not decorrelation, that's a problem, and we can measure that, which is a great way of finding out if you've got something going wrong. And we can use that correlation to identify proximate causes when we get this signal in. So this method incorporates user intent. We can produce data products that we can compare over time and combine. And then we can use these to actually find out when our systems are behaving badly, work out the duration and severity and impact of those things, which is really useful when you're doing postmortems, or critical when you're doing postmortems. We can compare behavior over time and chop it up over different dimensions if we need to do that, and actually directly measure decorrelation across different parts of our systems. And we have insights now that are not based on like randomly chosen thresholds, but based on actual principled analysis of the behavior of the platform. We've found invariants, we can track them over time, and we can have these building blocks that we can reprocess in many different ways. I work at Google. We have books. They're free. Go check them out. We're hiring. Thanks very much for your time.